Hello everyone, I'm Paul and today we're solving problem 2536, increment submatrices by 1. This is medium and requires some basic concepts, so let's go step by step. We are given an integer n representing an n times n matrix, so if n is free, we have this matrix. And we are also given a 2D integer array query, where each query has 2 points in this matrix. First we have the top left corner and then the bottom right corner of some rectangle. So for this query, we have this rectangle. And our job is here. We need to add 1 to every cell in within this rectangle. Remember that every cell is initially 0. So if we have this rectangle, we add 1 to 0 for each of these cells and we get this. Now we move to the next query and the current rectangle goes from cell 0, 0 to 1, 1. So we have this rectangle. If we add 1 to every cell here, we get 1, 1, 1, and 1 plus 1 is 2. And we need to return the final matrix after every query. So for this input, we return this. Now, maybe you are thinking about building this matrix and iterating each of these queries, and for each query running a nested for loop and add 1 to every corresponding cell and doing the same for every query. Now the problem is down here in the constraints. We can have up to 10 to the power of 4 queries, and for each query we can iterate over 500 times 500 cells as a maximum. So this is a lot. We need to think about something more efficient. And for this you should be familiar with something called difference array and prefix sum. So let's see how this works. Let's forget about this for now and let's say that we have an array with zeros, and let's say that we have some queries, and for each of these we want to add a 1 to everything that's in within this range. So for the first query we have 0, 2. We grab everything here and we add 1 to every element in this range. Now we have this query, so we add 1 to everything in this range. This is 2 and this is 1. So for this example, this is the final array. Now the question is, how can we get this in big O of n time complexity? Because we are trying to avoid iterating everything in within this range and then iterating everything in within this range, because here we have repeated elements. We are repeating work. So this is not efficient. We need to think about something else, something that runs in big O of n time complexity. And here is where we can use a difference array. This is an array with zeros initially, and here we are storing only the effects of each of these queries. Here we have 2 effects. From index 0, we add 1 to every element, and we keep doing this until index 2 included. So at index 3, meaning here, we stop this effect. So we can store these 2 effects here in our difference array. First, we add 1 to every value from index 0. So from here, we add 1. And from this index plus 1, meaning from index 3, from here, we stop the effect of this query. So at this point, we subtract 1. Now we do the same with this query. At index 2, we start adding a 1 to every element, and we stop at index 3 plus 1. So at index 2, we add a 1, and at index 4, meaning here at index 4, we subtract 1. And now with this difference array, we can build a prefix sum array, which is just an array where we store the sum of every element up to the corresponding index. First we have a 1, so we add 1. Next we have 0, so we take the accumulated sum plus the current value, and this is 1. Now 1 plus 1 is 2. Now 2 plus minus 1 is 1. and we don't care about this last value because this is just to build this difference array. So we end here. And in case you didn't notice, this is the result, but we are building this in big O of n time complexity, which is very efficient. So now let's see how can we use these two concepts, difference array and prefix sum, in this problem. Here we are doing exactly the same in matrices. So we have a difference matrix and the final matrix. And this difference matrix has one more row and one more column, exactly the same as before. And we are doing the same, so we iterate every query and we are storing the effect of each of these queries in this difference matrix. First we are here, we go from 1, 1 to 2, 2, meaning from here to here. So we have this rectangle. First we add a 1 here in the difference matrix. Here we put a 1. And what this means is we start an effect here. We will add a 1 to every cell from here to the right and from here to the bottom. And now we need to know where to stop with this effect, because if we leave this one here, we are adding a 1 to everything within this rectangle. But we only need this small rectangle. So we should stop this effect here and here. So here we put the -1 and here we put the -1. And now we have another problem. If we put a -1 here, this negative effect will go for this entire column. And if we put a -1 here, this negative effect will go for this entire row. So this cell will have a double negative effect. And if we want to counter this double negative effect, we need to add 1 in this diagonal. And just to be clear, by doing this, we are neutralizing one of these two effects. We are keeping only one of these, which is exactly what we want because we want this small rectangle, okay? Now we need to do the same here. We need to add the effects for this rectangle. It goes from 0, 0 to 1, 1, so we have this. So from 0, 0, we are adding 1 to every cell. Now if we only add this, we will add a 1 to every cell in this matrix, but we only want this small rectangle. So we need to add a -1 here, a -1 here to stop this effect, and we need to counter these two effects. So here we add a 1. And now we are doing what we want, which is to select this rectangle. Now we have a full difference matrix and we can move to the prefix sum part. For this, we will return this matrix and every element here is initially 0. We are iterating everything from left to right and from top to bottom. So initially we are standing here at this cell. Now the corresponding effect at this cell is 1, so we put 1. Next we are standing here and we have an effect of 0. And we need to add the accumulated effect up to this moment. And for this we can look left and 1 plus 0 is 1. Next we are here and the effect up to at this moment, at this cell, is -1. And we need to add the accumulated effect up to this point, so we do -1 plus this. -1 plus 1 is 0, so we put 0. Next we are here. We have an effect of 0 exactly at this cell, so we do 0 plus the accumulated effect up to this cell. 0 plus 1 is 1. Next we are here, and here it starts an effect of 1. So we need to do 1 plus the accumulated effect up to this moment. And maybe you are thinking about looking left and up. And if you do 1 plus 1, the result is 2. Now the problem is that if we only do this, we are adding the same effect twice. Because remember that these two effects come from the same place. They are both from this rectangle. So we are counting the same effect twice here. Now, if we want to counter this, we need to subtract the effect of the diagonal. So here we subtract 1, and the result for this is 2, so we put the 2 here. Now we are here and the effect at this point is 0, and we need to add the accumulated effect, so we do 0 plus 2 plus 0 minus 1, and the result is 1. Now we are here, we have an effect of minus 1, and the accumulated effect is here, it's a 1. And this is 0, so we put 0 here. Now we are here, the current effect is 0, and the accumulated effect is 0 plus 2 minus the diagonal 1. And this is 1, so we put 1 here. Now we are standing here, we have an effect of 1, and we need to add the accumulated effect, meaning 1 plus 1 minus the diagonal 2, and this is 1. So we put 1 here. At this point we can return the final matrix, and by doing all of this we are solving the problem in big O of Q plus n squared time complexity. Here Q is the amount of queries and n squared is because we are iterating the matrix. And space complexity will be the required space to build this, meaning big O of n squared. So with all of this in mind, let's go with the code. Here we need to build 2 matrices, one for the result, which we'll call M. This is an array which contains an array with 0 times n for every index in range n. And we are doing something very similar for the difference matrix. We will call this D. This is an array which contains an array with 0 times n plus 1 for every index in range n plus 1. Remember that here we need one more column and one more row. Now we can iterate queries, so for row 1, column 1, row 2, column 2 in queries, we have 4 effects per query. The start effect is at row 1, column 1. Here we need to add 1. Now we need to stop this effect for the same column. This is at row 2 plus 1, column 1. Here we subtract 1. And we need to stop this effect for the same row also. This is at row 1, column 2 plus 1. Here we subtract 1. Now we need to fix the diagonal. Remember the approach. This is at row 2 plus 1, column 2 plus 1. Here we need to add 1. And just to be clear, here we start. Here we stop vertical. Here we stop horizontal. And here we fix diagonal. Now we are ready to build the result. So for I in range n, for j in range n. We have the accumulated effect for the current column. We'll call this AC at, matrix at I minus 1 j. And it might be a case that this is out of bounds. So we'll say that we want this if I is greater than 0, else we want 0. Now we also have the accumulated effect for the current row. This is matrix at I and j minus 1, but once again, it might be a case that this is out of bounds. So here we add if j is greater than 0, else 0. Finally, we need the accumulated diagonal. And this is at matrix I minus 1, j minus 1. And this might be out of bounds. So here we say if I is greater than 0 and j is greater than 0, else 0. And every time we say matrix I j is the difference matrix at the same row and the same column plus AC plus AR minus the diagonal. And just to be clear, here we are taking the current effect effect plus the accumulated effect. Okay. Finally, we return matrix. So this is the entire code. I think this is right. Let's submit this. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.